Today, Jen and I are going to talk about load balancers. But before we begin, I'd like to thank Jeon, Bractlet, and Codesmith for sponsoring this Tech Talk. Here are some of the topics that we are going to touch on during the talk. First is a general overview of what load balancers are and why one would even use load balancers. Second are all the diverse load balancing algorithms that can be utilized for distributing traffic. Then we are going to talk about differences between hardware and software load balancers. Next, before discussing on application and network load balancers, we want to give some context by discussing on OSI layers, and finally end the presentation with an overview on the differences between application and network load balancers. Before we can dive deeper, we first need to understand what load balancers are. Load balancers can be pictured as a traffic cop that sits in front of your server pools and routes client requests in a way to ensure that no one server is overworked. This can create many benefits for those who do decide to deploy load balancers for websites and applications with many active users, which Jen will elaborate on.
So why load balancers? As Yohan was mentioning before, load balancers distribute incoming traffic across multiple servers so that no single resource is overwhelmed. By utilizing load balancers, we maximize speed, capacity utilization. It prevents requests to down servers, and we can add or remove servers with demand. By utilizing load balancers, we prevent any bottlenecks or point of failure that could lead to downtime or performance issues.
Here is a list of the most commonly used load balancer algorithms. Don't worry about remembering everything here. I'll be going through each one in more depth. First is the round robin, which simply serves requests to servers sequentially. For example, if there are 3 servers, the load balancer will send traffic to servers in the order they came. Server 1, server 2, server 3, and back to server 1, so on and so forth. Second is the least connections algorithm. For this algorithm, every new request is sent to the server with the fewest concurrent connections to clients. Pretty straightforward. Third, we have the least response time algorithm. This algorithm sends requests to servers with the fastest response time. It also takes into account both the server's current load and its latency. Next, we have the random algorithm. The name of this algorithm pretty much tells us how requests are distributed to servers, at random. Similarly, there is the random 2 choices algorithm, which picks 2 servers randomly and then applies the least connections algorithm on those 2 servers. A bit more complicated are the hash algorithms, which come in 2 flavors, IP hash and URL hash. The IP hash uses the IP address of the client to determine which server receives the request. This allows for session persistence. Also known as a sticky session, it's the idea that all requests from a client are sent to the same server for the duration of the session. This is necessary to prevent having to send information between servers or even possibly prevent data from becoming irretrievable. The URL hash utilizes the URL of the request, which is useful for caching purposes as requests for the same resource are consistently directed to the same server. On to Jen to talk about unweighted and weighted algorithms.
So unweighted and weighted. In load balancers, weight indicates capacity or level of importance. So a server with a high weight value indicates that it's more capable of handling a greater share of traffic. Using that context, you can tell that unweighted means that we're not taking weight into consideration. It basically assumes that all servers have the same capacity. Examples of algorithms that use this are round robin and least connections. As Yohan was mentioning before, round robin is when the traffic is distributed sequentially, whereas least connections is when it's being sent to the least active connections. On the other hand, weighted is when we do take those servers' weight into consideration. How this works is basically you're given a predefined weight value to each server. This allows allocation of more traffic of servers with higher processing power. So examples of these would be a weighted round robin and weighted least connections. So how a weighted round robin works is basically, let's say server A has a weight of 2 and server B has a weight of 1. Therefore, server A receives 2 times the request of server B. With weighted least connections, they're also assigned a number that's a ratio. So server A has a weight of 4 with 3 active connections. This gives them a ratio of 0.75. Server B has a weight of 2 with 1 active connection, which gives them a ratio of 0.5. So because server B has a lower ratio, it receives the next incoming request.
Before comparing whether hardware or software load balancers are better, let's understand what they are and how they function. Hardware load balancers are a hardware device with a specialized operating system designed for distributing traffic. They are deployed in on-premise data centers and are usually standalone pieces of hardware that runs load balancing software. Because hardware load balancers are not easily scalable based on demand, companies that utilize hardware load balancers must predict the amount of hardware load balancers needed. This amount must account for the peak traffic load as well as deploy them in pairs in case one hardware load balancer malfunctions. Software load balancers are managed by administrators. They are usually offered as one of many functions of the Application Delivery Controller, or ADC for short, that runs on a standard server or a virtual machine, or VM for short. They can also be prepackaged into VMs or can also be directly installed onto a server.
So now we're gonna go into hardware versus software load balancers. Most companies use a combination of both, but traditionally hardware load balancers have been the preferred due to the fact that they're highly performant and they're more reliable and less prone for failure. They're more highly performant since they're specially designed with dedicated hardware that can handle high volumes with low latency and consistent performance. Whereas, and they're also more reliable and less prone to failure because of that hardware that they're built on. So it's more optimized and well tested, and also built with redundant components such as power supplies, fans, network interfaces, which provide high values of availability, and fault tolerance. The operating system itself is also built with specific hardware to be compatible with the hardware load balancers, which allows for even more performance and stability. Even with all those great aspects, software load balancers have been gaining popularity in recent years due to their scalability, flexibility, cost efficiency, ease of deployment, and security. With scalability, we can add and drop virtual servers to the demand and respond automatically and in real time to fluctuations in network traffic. They're much more flexible because they're compatible in many environments. They're programmable to operating system, the cloud, and many more, whereas hardware load balancers are not programmable. They're much more cost efficient because they're considered operating expense versus a capital expenditure. This is cheaper because capital expenditures take a lot more money to acquire or upgrade physical assets because they need to get hardware or building infrastructure. OpEx, such as software load balancers, don't need these maintenance and scaling costs. So in terms of ease of deployment, they're easily deployed, whereas hardware load balancers are difficult and expensive to install. And because software load balancers sit between the client and the server, they add that extra layer of security. In addition, software load balancers can also be run on the cloud, where the service provider is responsible for installing, configuring, and managing it. And another benefit of it being on the cloud is that it can be hosted all around the world. So if something goes down in the northeast of the US, it can be redirected from other parts of the country where it can still be running.
Load balancers also have a more distinct classification known as network and application load balancers. Before discussing these types, we wanted to talk about the Open Systems Interconnection model, which I will now refer to as the OSI model. One strong distinction between the two load balancers is that the network load balancer operates on layer 4 of the OSI model, while the application load balancer runs on layer 7 of the OSI model. Each layer specializes in serving different forms of information. Layer 4, known as the transport layer, is responsible for making sure that data is delivered between devices in a reliable and orderly way. At this layer, data is broken down into smaller pieces called packets before being sent across the internet. It's also where basic rules are set up to ensure that packets reach their destination correctly. It's because network load balancers work in layer 4 that they handle simpler types of web traffic, such as TCP, UDP, and TLS connections. In contrast, layer 7 is known as the application layer. This is the layer where developers can code listeners into the application to react to specific events. And it's also the layer that many users interact with every day. Because of this focus on content, the types of web traffic that application load balancers work with include more complex and application-specific information. Some examples include URL cookies, HTTP headers, URL paths, or host names. Now that we have an overview, I'll hand it to Jen to talk about the big differences between the application and network load balancers.
So differences between network and application load balancers. You can think of this as a simple versus a smart traffic cop, with the simple traffic cop being layer 4 or network load balancer versus smart traffic cop, which is layer 7, which is the application load balancer. For simple traffic cop layer 4, they provide support for static IP, whereas layer 7 does not provide that support. Layer 4 gives a permanent IP address within each availability zone. However, it does not ensure the availability of the application. This is because it solely bases its decisions on network and TCP layer variables and has no awareness of the application at all. So when you're using layer 4, it's most suitable for simple and efficient traffic routing due to its high throughput and low latency requirements. Smart traffic cop, on the other hand, one of the bigger benefits is that caching can be implemented. This allows for reducing server load, which improves response time. It's also applicable for microservices and can perform health checks. And because it is content-based, it looks into the actual content of the application. So there's data decryption involved. In order to decrypt the data, it must share the TLS certificate between the client and the server. So for layer 7, it's most suitable for advanced traffic routing and management and application level features and customization. And just to quickly gloss over elastic load balancing, it takes advantages of both smart and simple traffic routing. So elastic load balancing can go directly from network to application load balancing.
Here are our sources, and hopefully you learned a thing or two about load balancers. If you'd like to connect with us, you can reach out to us on LinkedIn or GitHub through the QR codes on the screen. Thank you.